Yeah, it's a great pleasure to attend this very nice workshop to celebrate the achievements of these three physicists. I just realized very recently how much influence they have on my academic career so far. So before my talk, I would like to give a very brief review of what I did at the very early stage of my research. I received my PhD from Princeton University in 2004, and my advisor was Professor Paul Ng. He was born in Malaysia, so he used to visit Singapore very often. At that time, my thesis is on the Nernst effect in high-temperature superconductors. The basic finding is we found that in the anisotropic regime, I think this one, they are connected to another one. I think the other one is much better. Yeah. I don't need a remote, actually. Yeah, fine, thank you. We found in the anisotropic regime of the cuprates, there are vortices above Tc, and the basic physics is that in the anisotropic regime, the superfluid density is so low, and the famous Wimura plot tell us the superconducting transition temperature is proportional to the superfluid density. So it's very similar to what Professor John Rappi taught the other day about the superfluid helium. That's a strong indication that the phase transition is the QAHE type. And basically, in this regime of the phase diagram, where we have a very strong parent temperature and a very low phase stiffness temperature, there's a wide range of temperatures where they were pairing, but without long-range phase coherence. So we found vortex-like excitations by using the Nernst effect. And I think Professor Machedi mentioned some of this work in his talk the first day of the workshop. So at that time, although I was a Princeton student, I didn't interact very much with Duncan Hodin. I was a big fan of KT. It's after I came back to Tsinghua University in 2008 that my research started to overlap very strongly with Duncan's theoretical proposal in the early days. So today I'm going to talk about the transport and the magnetic properties in topological insulators with a broken time reversal symmetry. So this is a big collaboration, and the leader of this very big team is Professor QSHE. I think many of you have met him before, and Professor QAHE is a junior faculty in his group. He was in charge of the MB sample growth, RPAS, and STM measurements on these topological insulator materials. The transport measurement were done by my students at Tsinghua, and we also had theoretical discussions with many theorists around the world. So I'll start from the very beginning. This is the Hall effect discovered by Hall 140 years ago, where the Hall resistance is linearly proportional to the magnetic field. 2 years later, Hall measured magnetic materials and discovered the so-called anomalous Hall effect. Basically, the difference is even in zero magnetic field, there's a finite Hall resistance, which is proportional to the magnetization of the sample. So there's a hysteresis loop. And in 1980, we know that von Klitzing found the quantum Hall effect, and David Solis told us that the quantized Hall plateau is related to the topological invariant of the Landau levels. So basically, in the bulk, all the current carrying states are localized by strong magnetic field, and there are chiral edge state along the sample edge, which give you the quantized Hall plateau and the zero resistance. So because we need a very strong magnetic field to realize the quantum Hall effect, people start to ask, can we realize this same effect in zero magnetic field, which is much better for application? So from this very naive picture, it means that even without a magnetic field, somehow the bulk is insulating, and we will have this chiral edge state along the sample boundary. This seems too good to be true. And experimentally, what we look for is that even in zero magnetic field, there will be a finite Hall resistance, which is quantized. It will have this quantum resistance of 25.8 kilo ohm. So this basic behavior is very similar to the anomalous Hall effect, except now that it's quantized even in zero magnetic field. So that's the experimental signature that we are looking for the so-called quantum anomalous Hall effect. Of course, the whole story starts from Duncan's famous 1988 paper he proposed the so-called Duncan-Haldane model for a quantum Hall effect without the lambda levels. However, this model is very difficult to realize experimentally, so we have to wait another 20 years till another field, topological insulator, start to appear. So in 2008, there's this very interesting theoretical proposal by Chaoxing Liu, Xiaoliang Qi, Shoucheng Zhang et al. Actually, at that time, Chaoxing was a student, graduate student at Tsinghua. He visited Würzburg University and heard about this mercury telluride quantum well. And it was claimed by the Molecamp group that the quantum spin Hall effect has been discovered in this quantum well. Then Chaoxing said, wow, if you dope a magnetic impurity into it and make it ferromagnetic, you may change a quantum spin Hall insulator into a quantum non-Hall insulator. So that's his proposal. Unfortunately, this material, manganese-doped mercury telluride, has never been ferromagnetic, so quantum non-Hall effect was not found in this material. 2 years later, a new class of topological insulator, bismuth telluride, bismuth selenide, antimonide telluride, this so-called 3D topological insulator, became available. And this group, led by Xi Dai and Zhongfang, they proposed that this class of materials will be an even better system to realize the quantum anomalous Hall effect. So in this paper, the main contribution is they proposed a new ferromagnetic mechanism, the so-called Funk mechanism. They showed theoretically that in these materials, the system can be ferromagnetic even when the sample is insulating. That's very rare and is crucial for the realization of quantum anomalous Hall effect. So now let's take a look what we need to realize it experimentally. So this is a 2D topological insulator. We know there are helical edge state at the boundary. And Chaoxing Liu's proposal is if we start from this material and add ferromagnetic order into it, one of the helical state may be annihilated. So in the end, we will have a chiral edge state, which will give you the quantized anomalous Hall effect. Or we can start from the 3D topological insulator, which has this Dirac-like surface state, and make it very thin. When we make the ferromagnetic and insulating the bulk, we will also have a chiral edge state in the sample boundary, which will give you the quantum anomalous Hall effect. So in the end, we will need a two-dimensional ferromagnetic topological insulator. There are 4 requirements, and they are very tough for experimentalists because we know most ferromagnetic materials are metallic. You need RKKY to make the ferromagnetic. Very few of them are ferromagnetic insulator. We also know that ferromagnetism and topology, they hate each other. If you make it ferromagnetic, maybe you'll kill the topology. And to make all this happen in 2D will also be very difficult. So this is a huge challenge for the materials. Now let's have a look of the band structure. So before with the real space picture, we need the sample to be topological so that this is a bulk band structure. We will have the spontaneously generated topologically protected boundary state. Then we need to make the ferromagnetic, so there will be anomalous Hall effect, and it will open a gap in the surface state. And in the end, we will only have this edge state. We need to fine-tune the Fermi level, so it will only lie in this very small gap of the surface state, only cut through the edge state. So that will give you the quantum anomalous Hall effect. That we need to realize experimentally. And in order to grow these materials, Chi Kun's group used this very powerful machine. It's a 3-chamber UHV system. So they grow the thin film in the MB chamber, then transfer it in the UHV into the STM chamber to look at the surface morphology, then transfer it to the RPAS chamber to look at the band structure. Then they take the sample out of the UHV chamber, and my transport lab is just next door. So my student will quickly take the sample, scratch it into a transport device, and do the measurement within an hour or so. So this is a typical surface morphology of such a thin film. It could be very clean at the very small area, but over a large area, we will see these small islands or dips about 1 nanometer. It's a unit cell of the topological insulator. We grow the sample, the thin film, on the insulating substrate, such as a sapphire or STO, so there's no conduction from elsewhere. we cover the film with some capping layer to protect it against the contamination from the air. Then we cut the sample into a Hall bar geometry and do the transport measurement of the Hall resistance and the longitudinal resistance. So we start from these two topological insulators, bismuth telluride and antimony telluride. We dope chromium, the 3D transitional metal element, into it and measure the Hall effect. Immediately, we see very good anomalous Hall effect telling us, yes, they are ferromagnetic, and there's no problem about that. However, remember, what we are looking for is at the zero magnetic field, the Hall resistance should be quantized. It should be 25.8 kilo ohm. But now what we have is about 50 to 100 ohm. It's orders of magnitude away from the quantized value. So this is really bad. The reason is, at this regime, these two samples are not insulating. They are metallic. There are a lot of bulk carriers which will conduct, which will show the sample, the edge state conduction. And when we look at these curves carefully, we found that the chromium-doped antimony telluride had this positive ordinary Hall effect, whereas chromium-doped bismuth telluride had this negative Hall effect. So we thought, if we mix them together, this Hall-like bulk carrier and this electron-like bulk carrier, they may just compensate, and we could have insulating regime which will realize the quantum anomalous Hall effect. So here, let's have a look of the schematic band structure of bismuth telluride and antimony telluride. So both of them are topological insulator with this bulk inverted band gap and this topological protected surface state with a Dirac cone. However, these two materials have very different kind of defects. In bismuth telluride is tellurium vacancy, which will donate electrons into it, so that the Fermi level usually cut through the bulk conduction band. But for antimony telluride, the vacancy is anti-sag defect, which will donate holes into it, so the Fermi level usually cut through the bulk valence band. But they have very similar chemical and structural properties, so in principle, we can mix bismuth and antimony almost continuously. So that we believe at a certain regime of doping, the Fermi level will lie in the surface state without bulk conduction, which will be a true 3D topological insulator. So that's what we did, what we call band structure engineering. In fact, the idea is very similar in the 3.5 semiconductors, where people mix gallium arsenide and aluminum arsenide to achieve the band gap engineering, so that the fractional quantum Hall effect was discovered in the modulation doped sample. So here we have a series of alloys by mixing bismuth and antimony, and you can see on the pure phase on two ends, they are truly metallic because there are a lot of bulk carriers. But in the middle, at a certain doping ratio, the resistivity really give you an insulating behavior, because now the bulk carriers compensate each other, make it a true insulating. So that's a very important step towards the realization of quantum anomalous Hall effect. Then in these alloys, we dope chromium into it, and you can see at the two end, the Hall resistance is very small. This is multiplied by 5 or 10, so the true value is something like 50 or 100 ohm. But in the middle, when we are in the insulating regime, you can see it's still ferromagnetic, and now the Hall effect, anomalous Hall effect, is huge. It reaches 3 kilo ohm at a zero magnetic field. Now it's only 1 order of magnitude away from the quantized value, so we are very happy about this. Again, this is also a very strong indication that Fengzhou and Xidai theory is correct, because in this insulating regime, we still have very strong ferromagnetic order. So the fan-fleck mechanism should work in this regime. So after we got this, we know we are quite close to the quantization. But if we only have this chemical doping, we can only get the discrete samples. However, to realize quantum anomalous Hall effect, we need to have an accurate tuning of the Fermi chemical potential, the Fermi level. So we need to fabricate a transistor device so that we can use a gate voltage to tune the Fermi level very seriously. So we grow the thin film on the STO substrate. STO is the oxide with a very large dielectric constant at low temperature. So it could be used as a dielectric material. Then we put the electrode on the bottom of STO. So by connecting by applying gate voltage, we can tune the chemical potential of this magnetic topology insulator almost continuously. And again, this bring up another big jump in the quantum anomalous Hall effect. So in this figure, we show the anomalous Hall resistance as a function of gate voltage. You can see at the 0 gate, the anomalous Hall resistance at 0 field is only around 3 to 5 kilo ohm because the material is heavily doped. Then we can apply a positive gate voltage to inject electrons into it. And you can see immediately that the Hall resistance keep increasing. And at this doping range, it will reach a very large value, about 20 kilo ohm. If you inject more electrons into it, now the Hall resistance drop again, because now the Fermi level crossed a small gap of the surface state and cut into the conduction band. So only in this very narrow gate voltage, we will have a maximized Hall resistance. The curve is measured at 1.5 Kelvin, so we know all we need to get this quantized value, 24.8 kilo ohm, is to go to even lower temperature. So we collaborated with Professor Lu Li's group in IOP, because at that time, we don't have a dilution fridge in my lab. So in his lab, we performed the same measurements down to 30 millikelvin, and immediately we saw the quantized Hall effect. You can see that for this particular sample, if we apply a -6 volt gate voltage, the Hall resistance at 0 magnetic field is exactly this quantized value, h over e squared. And over a narrow gate range, it will remain over here so that there is a narrow plateau to give you the quantum anomalous Hall effect. But if you apply the gate voltage to either positive or negative range, you can see the Hall resistance will decrease because it's getting away from the quantized regime. So this figure tells us that by gate tuning, we can get a quantized anomalous Hall effect, just like expected. In the theory, it's almost like a square-shaped anomalous Hall curve. So here's a summary of the anomalous Hall resistance at the 0 magnetic field as a function of gate voltage. And you can see in this range, the anomalous Hall resistance really reached the quantized value and stayed there. Meanwhile, the longitudinal resistance had a very sharp decrease, meaning that the longitudinal transport along the edge is almost dissipationless. So these are the classical signatures of the quantum Hall effect, but now it's realized in 0 magnetic field. So this paper was published in 2013. It's indicated the observation of quantum anomalous Hall effect for the first time. So we are very happy that this figure actually was used in the scientific background for last year's Nobel Prize as figure 6. And it says that this phase of matter described by Hordin is not called the Chern insulator. And 25 years later, in 2013, a quantized Hall effect was observed in the film of chromium-doped bismuth annually telluride topological insulator at the 0 magnetic field, thus providing the first experimental detection of this phase of matter. Okay. And in the issue, when we published the report in Science, there was a perspective written by Professor O from Rutgers University, and he said that now, with the discovery of the quantum anomalous Hall effect, the quantum Hall trial is complete. So we know there are 3 types of Hall effect: the ordinary Hall effect, the spin Hall effect, and the anomalous Hall effect. So the quantum Hall effect was discovered by von Clising in 1980, and the quantum spin Hall effect was discovered by Molenkamp's group in 2007. And the last one is the quantum anomalous Hall effect, discovered by our collaboration in 2013. So it seems the quantum Hall family is complete now. But now I put a question mark over here, because over the last couple of years, there have some controversies about the quantum spin Hall effect. The quantum anomalous Hall effects have been reproduced by many groups in different topological insular materials. So now let's take a look of the quantum spin Hall effect. So this is where the first work by Molenkamp's group on mercury telluride and cadmium mercury telluride quantum wells. So they claim that they have found the quantized spin Hall effect by electrical detection. So quantum spin Hall effect refers to a pair of helical edge states. It's protected by time reversal symmetry, unlike the quantum Hall and the quantum anomalous Hall. Very similar phenomena was found out later by Reduce group in indium arsenide and gallium antimony, another quantum well material. However, if we look at the data very carefully, we found that the quantization is not so good because you can see this is the first paper by Molenkamp's group in 2007. In this log scale over several orders of magnitude, the Hall resistance seems to be quantized, or Hall conductance. But in the linear scale, when they zoom in, you can see this line is theoretically predicted 2 times quantum Hall resistance or conductance. But this black curve and the green curve, they are the experimental data at 1.58 Kelvin and 30 millikelvin. You can see there's no a real flat plateau as found in quantum Hall or quantum anomalous Hall. Actually, at lower temperature, the Hall resistance exceeds the quantized value quite significantly. So the data is not as nice as the other 2 cases. But this is not their fault because we know that it's actually really difficult to find a very good quantum spin Hall effect. The reason is that although these materials are 2D topological insulators, as predicted by Shouchun Zhang's group, there's a pair of helical edge state at the boundary, and in principle, backscattering between them is prohibited by a temperature symmetry. However, anything that can cause a spin flip will immediately cause very strong scattering between them. This includes magnetic impurity. This includes inelastic scattering at finite temperature. So in order to find this ideal quantum spin Hall effect due to the helical edge state, we need a very clean sample. This sample, the mobility is the order of 10 to the 5th. We need a very low temperature to suppress inelastic scattering. We also need a very small device. The probe distance should be smaller than the spin scattering length, which is around 1 micrometer. So this experiment is extremely challenging, very difficult. So this might explain why the quantization is not so good. However, a more serious challenge came later, last year. There were 5 groups from different places in the world, led by Charlie Marcus and Leo Copenhoven and George Falk, Marco Soklich, and Ken Moller, very highly respected groups in mesoscopic physics. They claimed that in this topological trivial phase of indium arsenide, gallium antimony, quantum well, they found a very similar edge state conduction. So here I took 2 sentences from this paper. They said that in the trivial regime, they can use 2 gates to tune the band structure of this quantum well to make it topological or trivial. They found that even in the trivial regime, Ball conductivity is quenched, but transport persists along the edges, superficially resembling the predicted helical edge channels in the topological regime. So they conclude that the observed edge channel conduction reported previously by the 2 other groups should be taken as circumstantial rather than direct evidence for helical edge states and hence the topological phase. So that really poses a serious challenge because experimentally, it's very difficult to distinguish a helical edge state and a trivial edge state. From a Landau-Büttiker formula for edge state transport, the transmission element or the matrix element for these 2 types of edge states are very similar. It's one for both directions because there's no breaking of temperature symmetry. But in quantum Hall and quantum anomalous Hall, it's very clear that in one direction is chiral. In one direction is 1, the other, the backward, is 0. So they have totally different edge state transport. But the helical and the trivial edge state look quite similar in some sense. So after we read this article last year, we thought, so the quantum spin Hall effect probably is not definitively discovered yet. So we thought we may have a chance to find another material to detect the quantum spin Hall state. And when we thought hard about this problem, we realized that a quantum spin Hall insulator, where there's a pair of helical states, is actually equivalent to a quantum anomalous Hall bilayer. If we have 2 layers of quantum anomalous Hall in which the edge state counterpropagate with each other with opposite spin orientation, then from the transport point of view, these are really equivalent. Although this is a 2D topological insulator with the temporal symmetry, but this is not. I don't care about that, but the quantum spin Hall effect should exist in this quantum anomalous Hall bilayer. Then the problem is how can you realize such architecture with this counterpropagating quantum anomalous Hall bilayer? And we had an idea, that is, if we have two different quantum anomalous systems with very different coercive field, so in the field range between these two coercive fields, one of the layers is already reversed, but the other is not. So the magnetization of the two films will be opposite to each other, which will give you two counter-propagating edge state. So that's our idea. Then the next thing is to realize this experimentally. And luckily, we found it very recently. So this is the data my students sent me after I arrived in Singapore. So these are two quantum Nonlocal insulators with very strongly different coercive field. This one has a coercive field around 0.2 Tesla, but this one has a one as large as 0.8 Tesla. And they both show very nice quantum anomalous Hall effect. So we believe if we make a double-decker, this bilayer of these two systems, in the intermediate field range, such as around 0.5 Tesla, we should be able to see the quantum spin Hall effect, and we did. So we bound these two samples into this double-decker structure and made this crossbar architecture, apply current from 1 to 3, measure the Hall voltage of 2 to 4, and that was what we found. In the very strong magnetic field, when both the two films have the same magnetization direction, this is the quantum anomalous Hall regime, just with two layers of conduction. So the total Hall resistance will be half the quantum Hall resistance. This is expected. And but in this regime, around 0.5 Tesla, when one of them is reversed, what we get is 0 Hall conductance, because these two counter-propagating edge states will cancel each other. So we believe in this range is the quantum spin Hall regime. By tuning the magnetic field, we can actually drive from quantum anomalous Hall to quantum spin Hall to quantum anomalous Hall again. Okay? Then later on, my student made into different direct structures, such as a pi bar, and did all kinds of non-local transport. And these values, these strange values of the quantum Hall conductance is consistent from the expectation for quantum spin Hall state. So we are still taking data to make it more complete and better. But we believe we already find a system to realize robust quantum spin Hall effect. So my student Yayu Wang is busy taking data and writing up the paper. And in the process of realizing quantum anomalous Hall effect, it's also very important to understand why some of the systems predicted by theory fails, why they are not very good quantum anomalous Hall system. So one of the examples is chromium-doped bismuth selenide. Bismuth selenide is perhaps the best 3D topological insulator in terms of band structure because it has a very large inverted bulk band gap. It's around 300 millieV. It has very nice dual cone surface state. However, when we dope chromium into bismuth selenide, we don't see any ferromagnetic order. The Hall effect behaves just like a paramagnetic order for a paramagnet, unlike chromium-doped bismuth telluride, where we clearly see the anomalous Hall effect. Bismuth telluride and bismuth telluride are very similar to each other in terms of structure and electronic structure. So we want to understand why this material, which was thought to be the best quantum anomalous insulator, fails. A trick we usually use is we mix them. We mix selenium and tellurium almost arbitrarily because they belong to the same group. And we can drive very systematically the system from ferromagnetic to weaker ferromagnet, even weaker, and in the end to a paramagnetic phase. And there's a critical doping level. When the selenium concentration is around 0.6, we will drive it from ferromagnetic to paramagnetic. So here we are seeing a quantum phase transition from ferromagnetic to paramagnetic. We also performed the RPS measurements of the different regimes, and in this topological regime, which is the tellurium-rich regime, we found very nice surface state, meaning they are still topological with this protected surface state. But in the selenium-rich regime, we found that the surface states are gone, and instead we found energy gap in the bulk band structure. So indicating that this regime might be trivial because now the surface is destroyed. So here, by doing this RPS measurement, what we're seeing is a topological phase transition from non-trivial to trivial, driven by selenium doping into tellurium. So we want to understand why. So we talked to our theorist friends, and they told us the reason is chromium substitution of bismuth not only give us a local moment, but also it will reduce the spin-off the coupling strength because chromium is so much lighter than bismuth. And we know in topological insulator, the band inversion is caused by spin-off the coupling. So when the chromium concentration is too large, it will drive the system from topological to non-topological, just because spin-off the coupling is too weak to invert the band gap. We also know that tellurium is much heavier than selenium, so it has stronger spin-off the coupling strength than bismuth selenide. So in this regime that we are interested in, where we found the quantum anomalous Hall effect, 11% of chromium doping will drive bismuth selenide into the trivial regime, but chromium doped bismuth telluride is still topological. So there's topological quantum phase transition as we tune the spin-off the coupling strength by varying the selenium-tellurium ratio in these alloys. And if we follow this theory paper by Fang Zhong and Xi Dai, that in this paper they calculated that the ferromagnetic phase is favored when the band topology is inverted, when it's non-trivial. So this is consistent. So in the end, the picture is by this doping, we change spin-off the coupling strength, drive a topological phase transition, and then is followed by a magnetic phase transition due to this fan-fleck mechanism. So that's what's published a few years ago. And later on, we thought at this doping range, the system is in the topological quantum critical point where the two bulk band gap just become zero. The conduction and valence band touch each other. So can we use the external perturbation to drive the system to topological or topological trivial regime? And most useful parameter or tuning parameter is, of course, the gate voltage, because that's what we use in a real electronic device. So we decide to do a gate voltage dependent study of the anomalous Hall effect in this particular alloy system. Again, we start from this tellurium-rich ferromagnetic regime. We found that when we apply gate voltage, it does nothing to the ferromagnetic order. The coercive field doesn't change. It's always a good ferromagnet, similar to here, although the magnetic property is weaker than here. When we go to another limit, the selenium-rich paramagnetic samples, again, this large gate voltage doesn't affect the magnetic order at all. The system remains paramagnetic in all of this doping range, and there's only a slight change of the value of the Hall effect. However, when we reach the topological quantum critical point for selenium concentration around 0.67, the gate is the applied gate voltage has a very strong influence of the ferromagnetic order. So in this regime, when we apply a positive gate voltage, inject electrons, or for a particular electric field direction, the system is paramagnetic. But when we apply a negative gate voltage, inject holes, or cause opposite orientation of the electric field, the system is ferromagnetic. So by using a gate voltage, now we are tuning a ferromagnetic to paramagnetic quantum phase transition. And this is a summary of the gate voltage dependence of the Hall effect. You can see about in this regime, minus 25 to minus 50 volts, there is a magnetic quantum phase transition. So our first reaction when we look at this data is, oh, you are injecting carriers into it, so you will cause a change in the RKKY interaction caused by attenuating electrons. But that's not the case, because first of all, these material are heavily electron doped. The Fermi level cuts through the bulk conduction band. Secondly, we can look at the auditory Hall effect. The slope doesn't change very much, so we don't really change the carrier density very much. However, at the low field, we clearly see this magnetic phase transition. So it must be something else, not due to the injected charge. Now, if we compare the gate voltage dependence and the selenium-tellurium doping dependence, actually now there's a very strong resemblance. We have explained that this is caused by the topological phase transition, then followed by magnetic phase transition. So we believe the physics here could be very similar, but we need more help from the theorists. So we talked to Shoucheng Jiang and Jing Wang's group at Stanford, and they said it could be due to the so-called Stark effect, which is the shift of the energy level by applied electrical field. In fact, there were previous theoretical calculations by Kim's group in 2012. They show that when you apply an electric field perpendicular to the topological thin film, it can shift the energy levels to tune the system from topological to trivial, because basically you just need to invert the band gap. And these people, Yayu Wang, Biao Lian, and Shou Cheng, they performed a theoretical calculation based on our realistic materials. They found out that indeed for the for the electric field close to what we use in our experiment, there is a topological phase transition. In this part, the band gap is inverted, but due to the Stark effect, when the electric field is strong enough, it will shift energy level to cause it non-inverted, make it trivial. And because the magnetic accessibility is strongly correlated to the band topology in the fan flag mechanism, that will cause a magnetic phase transition. So that's what we believe is going on. I'll just give the last part, which is related to what Christos Papadopoulos talked the other day. It's about the Skyrmions. So in the topological insulator, now we found in this material, manganese bismuth telluride, we found a change from a simple anomalous Hall effect for 5QL sample to topological Hall effect in 4QL sample, and back to the anomalous Hall effect in 3QL sample. So by simply changing the thickness of the sample, we can create and destroy the topological Hall effect related to real space barrier curvature of the electrons when they carry around. So I don't want to go into the details, but basically we think the physics is that for topological insulator, when we make the very thin, the two surfaces will start to hybridize. That will change the band structure, and that will change the DM interaction, which is responsible for Skyrmion formation or the other non-planar magnetic property, which will give rise to the topological Hall effect. And we have theoretical calculations to confirm this conjecture. So I'll just summarize. In this talk, I show you that how we use the magnetic doping into topological insulator to realize the quantum anomalous Hall effect, to realize now in a quantum anomalous bilayer the quantum spin Hall effect. We also can change the topological and the magnetic phase transition by either doping or a Stark effect with a applied electric field. And that's all, and thank you very much for your attention. The gap size of the surface state.
Oh, well,
Yeah. We haven't done that. We are at the base temperature because we really want to get the best quantum spin Hall. Yeah, it's a 20 millikelvin. But for the quantum anomalous Hall effect, people have measured, like Goldhaber-Gordon's group, it's a very small gap. The gap size is only less than 1 Kelvin.
Are you using the same materials?
Similar, yeah.
Yes. I just want to comment that last month I went to a conference and Pablo Jalillo from MIT, he did this quantum spin Hall measurement in 2D materials called 1T prime tungsten ditelluride.
Yeah, I am aware of that work. Yeah.
Okay.
But the physics is very, very different from this.
Yeah. I think they also don't have a very well quantized.
Yeah, I saw the data. They already put it on archive. It's not a very well quantized.
But they claim to see it up to 100 Kelvin.
Yeah, it's also very strange because I think inelastic scattering will destroy it. I went to MIT last month and talked to his postdoc, and we discussed about this.
Okay.